Okay, so today will be our last lecture section for the protein, and we will go ahead and talk about the gel formation. So we call it gelatation. So that means we talk about gel formation. We need to know there are lots of the food products which is a gel formation. So for example, we talk about yogurt, we talk about egg mayonnaise, we talk about tofu, and we even talk about cheese, and it still can count like a gel fermented products. Now, what is gel formation? We can simply say this is an immobilization of a large portion of water. So how large it is? And you cannot believe it, it is around 95 to 98% is water. And it is intermediate status between liquid and solid. Now, when you have this formation, you also, of course, you need some of the chemicals, and the chemicals are going to work around. So there's another thing we can say. It is basically is hydrogen bonds works with those amino group or carboxy group in a big water, they say a big water pool. They just say it like that. Question. Okay, or a big water hole. The gel formation they also rely on is, we say, is a chemical interaction. So they rely on, could be hydrogen bonds that will make it weak. It could be covalent bonds, will make it strong, and it could be ionic bonds, which makes it intermediate. And they going from the status, lots of time we say it's from soil, solidified to like a pro-gel status, and then go to the gel status. And the overall, we can say this immobilization of a larger water let it become characterized by elasticity, plasticity, and viscosity. So that is what it looks like. Dr. Kenny mentioned about the formula, so we can talk about that. What does that mean? There is a standard formula to talk about the gel formation, which starts from NPN. So what the N means, this is a number. Okay, usually it means the molecular number of the protein. P means protein. And that means natural status. Now, in order to do the gel formation, we can say basically they need to go through the first step is, of course, is heating. Okay, so they heat it. So therefore, we can say the gel formation, there is something we need to do. The first step is denaturing. Denaturing using, for example, using heat. Now the second step is matrix formation. And the matrix formation, they rely on these chemical interaction. Hydrogen bonds, covalent bonds, ionic bonds. So you heat it, then denaturing. When the denaturing becomes N, P, and D. So obviously here you can say this D means denature. Or we can also say unfolded, because when we fold it, its protein usually is in organized. When it's denatured, it's unfolded, not in organized status. Now when this comes, they could go this way. If it's cooling down, they will become what is PDN. And this will become, we call it a soft translucent, or we say transparent gel. Now, it could also go the other way, which is go all the way on the top. It could be aggregated. If it's aggregated aggregation, then become a coagulant gel. A coagulant gel, which all of course, which means it's opaque to light, so it is untransparent. It's pretty screwed up together. And we know that if it's using cooling, become a soft, translucent, or transparent gel, they can always go back. So this is reversible some of the times. And then we can give you an example, which is a gelatin gel. And gelatin gel usually is heated, and then it could become back, and that means reheat. So here you can say this is reheat. Go to the denaturing status. So this is, you can say, solution or solid status. This has become a pro-gel status. And finally, this has become gel formation. So this is a formula, what Dr. Kenny mentioned, what it looks like. When we talk about the gels, there is a several category we can mention. We can discuss about that. So the first one, we talk about aggregated gel versus transparent gel, or we say soft gel. Let's say transparent gel, let's say soft gel, or clear gel, sometimes we say. What this means, there is two things we want to say. First of all, aggregated gel, we gave you an example. If it's by casing, then it's aggregated gel. If it's used manufactured from wheat protein, then it is a transparent gel. That's one of the examples. Second thing we want to mention, it depends on certain amount of the amino acids. If you have valine, phenylalanine, leucine, isoleucine, proline, the amino acid sequence and the amount is more than 3.2 more %, then we will say this is most likely will have an aggregated gel. Otherwise, you will have a transparent or clear gel, but it's not only decided by that. Sometimes you have these amount of the amino acids lower than 3.2. However, you have other things. For example, you may have a cross-linking will be generated. That's what we just mentioned. Let's say the product is reaching cysteine or cysteine, and we mentioned that we'll have a cross-linking. Because here you have a disulfide bonds. Is that right? Here you have a sulfide bonds, or hydroxy sulfide bonds. Those will make it also become an aggregated gel. Now for the transparent gel, lots of the time we can see those they have a relatively a high water holding capacity. So their pH value lots of the time will be avoid close to the PI isoelectronic point value. Because if you're close to the PI, sometimes you end up with a very low water holding capacity, and here you have a high water holding capacity, which means transparent and clear gel obviously can be absorbed in lots of the water. Okay, so these are some of the items we can mention about is like aggregated gel and the clear gel. Then we have what to talk about is reversible gel versus unreversible gel. This is pretty simple example will be reversible gel we just mentioned about gelatin gel is reversible. Unreversible, you have egg mayonnaise that is unreversible because egg products when you cook it certainly cannot put it back. So that's very obvious. From the chemical standpoint, we already mentioned several times. Most likely the reversible gel is composed by or connected with hydrogen bonds, and that is easy to understand because very low energy needed to break down that. And the unreversible gel could be coagulant, could be the covalent bonds because that needs more energy to break down, and lots of the time it is hydrophobic. And the reversible gel, lots of the time, it is hydrophilic. And we also mentioned about here, for unreversible gel, this is usually cross-linking will be forming SS, SH, and here, not necessary. Most of the time, we don't have the cross-linking. Okay, so that's reversible gel and unreversible gel. In reversible gel, like lactogluburin, lactoalbumin, it's an unreversible gel, and we will mention when we talk about the protein, milk protein. Now the next one what we want to say is what are the factors affected gel formation. When we talk about the protein, because gel is formed most likely by protein, then something is obvious is protein molecular weight. So the first factor obviously is molecular weight, MW, of the protein. In order to have a gel formation, the molecular of the weight has to be large. If the molecular weight is more than 23,000 delta. Now, obviously, 99% it could form gel. If it's less than 20,000, most likely it's not going to have the gel formation. It's only a liquid. But how about if it's between 20 to 23,000 delta? This could happen or not, depends on, rely on presence of disulfide, sulfur hydroxy, also rely on existing calcium, magnesium, we call it divalent ions. We'll give you examples. Those ions later on. Those ions are important if the molecular weight is not good enough. This is the first one. Second thing, we talk about the molecular weight of the proteins. Then we also want to make sure the gel formation, we have enough protein. Therefore, the concentration is important. So concentration of protein is the second major factor. Here we have a formula to talk about that, which is also related to how strong the gel will be. So we're using a G, ZB equals the concentration, original concentration of the protein, and also minus the concentration of L, least concentration in the point. And then times the power of n. This n is equals 1 to 2. That's physics. That's a physical chemistry. That's the most difficult class in the chemistry area. So we won't want to go deep of that. This guy here, which means least concentration in the point. There are fixed number for that. Usually, like soybean, if the soybean protein forms the gel, at least like 8%. If it's egg albumin, they require to have 4 to 5%. If the gelatin gel, that's not have much higher requirements, about like 0.5 to 0.6%, it can be from the gel. So these are something I wanted to tell you. The concentration is important. So we have a molecular weight, we have the concentration, what else? Obviously pH. pH is always important. Same as we talk all the time, the pH is better around 6 to 7 at a neutral status. We should avoid PI, or we say IP. Okay, because that will end up with lots of the precipitation. Which means by the time, if you are really the pH at PI, if you are making a reversible gel, that will not be successful. If you want to make an unreversible coagulant gel, then you should get close to PI. So sometimes this avoid that language to take it out, it depends. Because when you have a PI, you have a coagulant will be created. Okay, now last one. Avoid, or we say limit prolytic or protease or prolytic, which means avoid the function of protease. Because if we have a protease there, that's not very good, which means in the formula, we urge find the gel formation, but at the same time, the enzyme is working and they'll break down those proteins. That's not nice. So this have to be avoided. So, give you some of the examples. The first example is egg mayonnaise. This is what it looks like. So first of all, we call it, this is oil to water emulsification. We'll get to that in the lipid section. The second thing we want to say, this is the denaturing is egg white protein. Sorry, egg white protein is a major protein to join the gel formation. We need the denature, and the denaturing status chemicals of acylic acid. So therefore, we can use two different types of the acid. Lemon juice, which is providing citric acid, and we also can use vinegar, which is give you acetic acids. And once you have acetic acid, citric acid comes out, they could cause you cross-linking sometimes, or denaturing, then we'll generate droplets. And those droplets will be the mix of the egg white protein and with water and with other things. So usually those existing on the surface. That's what the egg mayonnaise looks like. Okay? Or we say emulsifying droplets. So the next example, we want to let you know about the manufacturing of the tofu. To tell you what it looks like. Manufacturing of the tofu, we coming from the soybean. So we get a soybean, which is yellow, color the soybean. We let them be soaked in water. Okay, then what we do, we're going to be crush it. So we crush it. Crushing, become a mixer. Of course, you need water. Then what we do? Obviously, you have to heating, or we say boiling, 95 to 100 degrees Celsius. Then what you get? Soil slurry. Then sometimes you go filtration, sometimes not. Then we become soil milk. Okay, once you have the soil milk, you're gonna have to do something. This is an important step. Once you have a soil milk, we have a liquid there, but we don't have that coagulant status. What we have to do? We reheat. Reheat a little bit lower temperature at 75 degrees Celsius. But what we need to add is what we are writing here. We talk about we need those divalent ions, which is with calcium, magnesium, lots of the time is sulfuric, calcium, magnesium, divalent ions. This will cause what kind of thing comes out? We call it a curd will comes out. And once the curd comes out, we'll do it in the press. The press will have two sections. One section, we call it a waste, but not really, it's wheat. Then the other one, we call it the curd, the purified curd, or we say it's cake, quotation mark cake. Then we go what? Coring process, and finally become a tofu. And the very important thing is the soil milk has been formed right here, are the important steps when you have the tofu manufacturing process. Okay, so that's an example of the geoformation, how they find it. Next one we want to talk about is the milk protein and the soybean protein, but we are going to go into really briefly, then we're going to go over the slides to talk about it. So milk protein. Lots of people know the major components of a milk protein is actually a casein. That's everybody knows. And we are doing in the lab for the microbiology class. We have the agar, we put the casein, and we also want to see bacteria will generate the caseiness. So we split onto two. One side we add we had E. coli, the other side we had the bacillus. Then after incubation, we will see one side become a transparent zone, which means casein is hydrolyzed casein, become a peptide. So casein is one of that. Now another thing what we also know is like a wheat protein. Okay, so what are those things? Where those come from? And we could do a simple experiment to isolate them. So let's do that. Is that the milk protein? The milk protein usually it is about 3.2% in a milk. Usually it's not like much. They going through the first process. It's very easy. Is using acid, adjust the pH at 4.6. It's a very interesting number, 4.6. The temperature is also important at around 20 degrees Celsius. So what this means? This means for the casein, the PI, or we say IP, is equals 4.6, the isoelectronic point, which means it will cause precipitation. So therefore, we're going to have something comes out. Yes, the casein will comes out. That's precipitation. This is huge, the precipitation part. That's usually more than 70 to 80%. Accurately say 78% is casein. Now you have a filter part, which is the supernated zone we can say. It's a filter one. Is wheat protein, or we say cereal protein. And basically it's wheat protein. Now the wheat protein, what we do, we first are going to do, this is around 17%, okay? We first are going to do some process. This time around, we can do is 0.5 saturation with ammonia, sulfur oxide, we say, and all is fully saturation with magnesium sulfuric. So once we have this one happens, we also got to do two sections, which is precipitation and also the filter part. And the precipitation will comes out beta lactoglobulin. And the supernatants, or we say filter part, this will comes out lactoalbumin. So that's how we do the research, how we do the experiment, a simple experiment. Now, of course, these days, they have those technology could find those sequencing, like casing, like whey protein, what are the sequence? Now, whey protein is also important. We have the joke, we says, if you have a cheese, just say we melted it, become 10 liter, 9 liter of whey protein, add 1 liter of water. So that's like a joke to talk about the importance of the whey protein. So with this figure, we can also using a table to talk about milk. So how are we using a table? We have casein 78%. Then we have whey protein 17%. Then the whey protein have lots of ingredients. We mentioned the two here, beta lactoglobulin. We have lactoalbumin. We have immunoglobulin. This is globulin. This everyone knows, Ig. And we also have called serine albumin. Kind of the beta lactoglobulin is the most dominant part. They will be around 8.5%. Lactoalbumin about like 5%. These two not much, 3 to 5%. So we have a 78%, 17%. What are we missing? There are 5% missing. What's that? This is N nitrogen containing but non-protein compounds. This makes the thing very tricky. Milk protein, there is a certain standards. The milk, they have a certain standards, or some dairy products, is the amount of the protein you need to reach certain level. The way they testing in the commercial area, they are not really doing the experiments or run the gel electrophoresis to see those bands like we did in the lab. They lots of the time is measuring the nitrogen amount. If the N amount is which certain level, then they think the protein reach certain concentration, so it's passed the test. However, we need to know, in the milk protein, there are 5% of the N containing but non-protein compounds. Because of that, people are going to be add more of this or of that kind. Sometimes even intoxication chemicals will be added. That makes a big importance of the milk scandals. You can talk about milk scandals happened in China in 2008, which has happened lots of the kids. We have a kidney disease, bladder kidney disease, all kinds of things. Because originally you have 5%. We can add some chemicals, make it become 10 or 15%. Because anyway, when you test it, you are using the N, the amount of the N as your standards. So that makes it very tricky. So this makes about 100%, but not really. Sometimes we had around 1% is enzyme. So enzyme, which is encoding like amylase, very little bit catalase, all kinds of oxidase. like peroxidase, those are one of that. So there's 1% of the enzyme. Okay. Now we want to talk a little bit about this casein. So what is casein? Casein is very interesting. This is a phosphoprotein. It is a phosphorylated protein. And the casein, basically, we can say it's very sensitive to calcium. What means sensitive? When you add the calcium, it will cause precipitation. So a very simple formula is you have a protein, you connect it with a phosphate, and then you with calcium, and then what do you become? Is a protein combined with phosphate, and there's a calcium there. And this whole thing causes precipitation. So calcium overall is a phosphoprotein, but does not mean all its components is phosphoprotein. So casein, basically we have alpha S1, alpha S2, beta, and carbocasein. This is not K, it's carbocasein. So the ratio of alpha S1 and S2 may be different. The amount is maybe different in different dairy or milk products. But the ratio is very interesting. It's always 3:1. And the ratio of the beta casein and the carbocasein is also interesting. It is 4.5 to 1.5. In other words, it's pseudo 3:1. It's the same thing. And the molecular weight of alpha, S1, S2, and the beta, these close to 24 to 25K Dalton, and the carbocasein is very low, is only around 17 to 19K Dalton. Now, if we want to discuss more about these, so alpha S1, this is very calcium sensitive. Now, both of these alpha S1 and S2 are sensitive, but alpha S1 is very calcium sensitive. Alpha S2 is highly phosphorylated. Then you have a beta. This is intermediate calcium sensitive. Not somehow between. But what happened is, it's a very sensitive for the temperature. At 4 degrees Celsius, it's a monomer. However, if you increase to 8 degrees Celsius, it will contribute, become a polymer. So it is interesting. And then when you go to the carbocasein, that's a different story. It is non-calcium sensitive. So these are the information we want to talk. Now for the casein, it's also we are interested to know they have a standard sequencing of the amino acids, which means they are first structure. The first structure, primary structure, is always serine X. That can be any of the amino acids, and then go to A. That could be glutamic acids. So that's what we are talking about the casein. Then we have the others. We don't want to dig a hole too much about these, okay? Something interesting is lactogluburin, lactoalbumin. Those, which is an AB variant, kind of like in the microbiology class, we talk about AB toxins. They have AB subunits. Now, casein, you have alpha S1, S2, beta carb, different type of that. They have the AB variants. The molecular weight somehow like 14 to 17K. But my standpoint is that I used to work a little bit when I was master students, is beta-lactoglobulin have antimicrobial function. And the casein here, if you use pepsin to hydrolyze it, to stimulate what the food's going to the intestinal area, you're using pepsin to hydrolyze at 37 degrees Celsius for 2 hours. Will generate a peptide. The peptide also has antimicrobial function. So just want to let you know I'm a microbiologist, I'm more interested about something from the milk protein. They have antimicrobial activity. And these research has been done in the last 50 years. Did a lot. And also I want to let you know, isolation of a milk protein is very difficult. What we here get is a very crude isolation, which means the purity is low. It's usually 60, 70%, 80%-ish. If you get more higher purity, that's very hard to do. And also there is a lot of the high molecular protein, and they are the functional protein. So milk, it actually has lots of the things we can talk about that. Okay, so we just be a little bit brief about here, but then we want to talk about one thing is interesting. Is about the sorbin protein. I don't have much space. So this is what we started, when I started to do for the microbiology research. So sorbin protein, that's in China, sorbin is a popular one. They have a different category based on their molecular weight, precipitation rate, we're using S, Vandenberg subunits, to express it. So we have 2S, 7S, 11S, and 15S. Now so far, they have not many research done for the 15S. So we write ANA. We don't know what the detail about that. 2S sorbin protein, they have some trypsin inhibitor. Lots of people find it. Even they find a higher amount of cytochrome C there. Very interesting. And then the 7S, which is a sorbin globulin. And what is this sorbin globulin? Called a beta carboxylate. So they are type 1 beta carboxylate. There is a type 2 beta carboxylate, and they also have a type 3, we call it gamma carboxylate. Now what is 11S? This is glycine. So that's a sorbin protein. Now, very interesting is I have been done that research 20 years ago to talk about beta carboxylate. So next I will be showing you in the slides briefly what we did long time ago. That's what we started have the for the microbiology